Okay, so now we are going to talk about cross-validation. So this is basically the main part of the lecture. Recall that the setup is that we have some random variables, and one random variable y is our response variable, and the rest of them are called x. So there are p of them, x1, x2, and so on up to xp, usually x1, x2, and so on, xp. So together they form this vector x. So they are predictors. And we assume that there exists a kind of the theoretical mechanism that generates this data. So this theoretical mechanism or the true model f, in practice, it is not known, right? But just in order to explain this material, in order for us to understand what's going on here, most of the time in today's lecture, we are going to work with simulated data, not with real data. So by the reason is that when we simulate our data, we know the actual f. Okay, so let's continue. So we are going to pretend that this true f is not known, and we are going to try to fit polynomial models of higher and higher degree. And so notice that every next one is strictly more flexible than the previous one. So for example, a quadratic model is strictly more flexible than the linear model because, you know, quadratic model includes linear models. So it may happen that B2 is 0, and if B2 is 0, then we get the original linear model. But we cannot get the quadratic model from the linear model, right? So a linear model is like a particular case of a quadratic model. Quadratic model is a particular case of the cubic model, and so on and so forth. Right? So, which is why what we are going to see is that the more flexible the model is, the more predictors we have, the training error is going to be smaller, strictly smaller. And this is what actually happens. So we are going to fit our model on some training set, simulated training set, and evaluate its mean squared error on some test set, also simulated. So here is the first example. So the truth here is the blue curve. And this blue curve, so you see it looks like a parabola. It's, as far as I remember, it is not exactly a parabola, but it kind of has this shape. Then we have three fitted models, so polynomials of degree 1, 3, and 10. And the one of degree 10 is actually the red one, right? And you see it's kind of wiggly, right? So it kind of goes up and down a lot. This happens with polynomial models of high degree, so they just tend to be kind of wiggly. And since the true model it resembles a parabola, this is why a fitted polynomial of degree 2 is actually a very good fit, right? So if you look at the right plot, you see that the training and test errors for a linear model, so when degree is 1, are quite large. But when we fit a quadratic model, so degree 2, training and test set errors both go down immediately, very, very quickly. So after this, as expected, the training error goes down monotonically. So every next step is going to give us a slightly smaller error than the previous step. So it always goes down, it never goes up. But for the test error, so the general trend here is up, and yet sometimes it just goes down a little bit and goes up a little bit. So that the actual smallest value is not 2, it happens to be 11, I believe here. And the polynomial of degree 11 is slightly better, seems to be slightly better than a polynomial of degree 2, but this is probably just because of the size of our training set. And maybe if we try to do it differently, if we split it into in a different way into training and validation set, we would get slightly different results. The main point is that the training error first goes down, and then after this, the training error always goes down, and the test error first goes down and then goes up, but non-monotonically. So this is different. Next example. So here, basically, you see the same thing. The red line here is a polynomial of degree 10, and it looks like kind of it's wiggly. So which is expected. Then the training error. When we increase the degree of our polynomial, so the training error always goes down. So everywhere it goes down. Sometimes just a little bit, sometimes by, well, significantly, but it always goes down with every next model here. It always goes down. The test error first goes down, right, and then goes up, but non-monotonically. So the best value, so the one that minimizes our test error is 4, right? So is degree here, the optimal degree is 4. All right. So notice that in both these examples, the training error is, of course, lower than the test error, and this is what we expect. So it should be lower. So in the next example, the true model is kind of, it looks, as far as I remember, it's part of a cosine or something like this. It's some trigonometric functions. Still, we would do the same thing. So we begin with a linear model, so quadratic model, and so on and so forth. And of course, so here a linear model is going to be a pretty poor fit because our curve, our true model, just goes up and down. And the red curve, which is the polynomial of degree 10, still looks a bit kind of wiggly. So notice that here, if we look at errors, the training error and the test error, that there is some range of degrees for which the training error seems to be worse than the test error. So the training error is just bigger. Sometimes it happens because, again, this might happen just by pure chance, especially if our data set is small. And here, our data set is not very large, it's just 100 observations, I think. So this is possible, right? This is possible. It's not usually the case, but sometimes it happens, and just due to random chance. If you work with, I don't know, super huge data sets with, I don't know, hundreds of thousands or millions of observations, especially when you do artificial neural networks, then it's not going to happen, probably. It will be very weird, but for small data sets, it may happen. It's not common, but it may happen. And still, the general trend is the same. So for the training error, we see that it always goes down. Every next step, it goes down. So goes down, goes down, goes down. Sometimes a little bit, sometimes significantly, but it always goes down. For the test error, first goes down, it reaches minimum somewhere here. For this example, it's the best degree is 5, but 3, 4, 6, and so on. So they do not look really very different. So probably it's just because of our particular choice of the training and test split. And then it goes up, right? But again, it does not go up monotonically. Sometimes it just goes down a little bit and then goes up again. So again, this is random, so it may happen. Okay, so recall that in tutorial 1, we did this bias-variance trade-off. And according to this bias-variance trade-off, when we fit a model on some training set, the error for a new test observation can be decomposed into these 3 sources. So it's the variance of our fitted model, is the bias of our fitted model, and is the variance of the random noise in the true model. So this bias error occurs due to the fact that our true model is not the same as our fitted model, because we never know the true model, so we don't know what the real f is. So we can only guess, right? And if our guess is close to the truth, then our model is not going to be biased a lot, right? So this bias tells us how closely we are to the truth. And variance occurs due to sensitivity of our algorithm, our model fitting process to random fluctuations. Now, so typically as flexibility of our f hat increases, our so f hat is our fitted model, right? So fitted the model, we fit the model f hat of x, not x hat. Sorry about that. Variance increases and bias decreases. So why is that? So I'll just give an example. So if, say, our true model is something like this, right? Then if, say, we want to fit some simple, like a linear function, then no matter how we fit it like this or like this or like this, we are never going to get the a very good estimate. So that there is always going to be some bias. So the bias is by how much our guessed model, our assumed model misses the true model. So this is bias. But if our algorithm is more flexible, right? So suppose that, I don't know, our algorithm is, say, quadratic function, then probably, so we're going to come up with a parabola that resembles this shape, and the parabola could probably be much better, so much more close to this shape. It's something like this. So which of course reduces the bias, because the bias is basically the distance between the true model and the fitted model. But at the same time, of course, the more flexible your model is, the more parameters it has, the higher is the chance that it's just going to approximate random noise rather than the true patterns in your data. And the problem with this bias variance trade-off is that so models that are highly flexible, they're going to minimize the bias, but they're going to have huge variance, and which is why they're still not very good. So, and the practical challenge here is to kind of to find a golden middle. So something that is neither not too biased, not of too high variance. Okay, so here is a little quiz for you on the first part of this